Hi, in this video, we're going to talk about generalization of the Simon's algorithm. Recall that in the Simon's algorithm, we have a function f going from 0, 1 power n to 0, 1 power n, and we are given the promise that f of x is equal to f of y if and only if there exists a secret period S such that X XOR S is equal to Y. So this is our period, which is unknown. And the goal of the Simon's algorithm is to find the secret period. Now, we know that we have a circuit for the Simon's algorithm, and we have to run this circuit repeatedly to find the secret period. And in one run of the algorithm, suppose I have, let me call this S, which consists of 0S. So this is a subspace of Z2 power n. And in each run of the algorithm, we get a number, let's say Z1, we get a number Z1 such that Z dot S is equal to 0, and so on, right? In n runs, we get n independent vectors Z1, Z2, Zn such that Zi dot S is equal to 0. And therefore, what we get is element of Z perp, or the orthogonal complement of Z of S. And if we get all these vectors Z1, Z2, and Zn as linearly independent, then we get a set of linear equations which we can solve, and then we get to the Simon's solution, right? We get the secret integer S. Now, there could be a generalization of this that let's say we have a function again from f 1 power n to 1 power n. And now we have the promise that f of x is equal to f of y if and only if um, x minus y belongs to S. And now in this case, S is a subspace of Z to N as before, but instead of being um, just a subspace which is one dimensional, in this case, we have an m-dimensional subspace. So Z is the span of, let's say, S1, S2, and Sm. So our goal is to find this basis of the m-dimensional subspace S. Given the promise that f of x is equal to f of y if x minus y belongs to S, right? And so one can think of this as a function, f, which is constant on the coset. So suppose this is a subspace, then you have these cosets, right? Y1 plus S, and right. So you have cosets, and the function is constant on the cosets, right? And so the goal is to find this subspace or subgroup of Z2n. So goal is that given a function which is constant on the cosets, we have to find the unknown subgroup S, right? So let's go to the circuit, the Simon circuit, right? We have this, let me draw the Simon circuit. We have the Hadamard power N, and then we have this oracle U of F, and these are multiple wires. So this is 0 tensor N, this is also 0 tensor N, and then we have a measurement here, and then we have a further Hadamard tensor N, and then you have the final measurement over here, right? So this is the Simon circuit. So recall, after this measurement in the Simon's algorithm, we get uh, some vector that looks like this, uh, y plus y plus s over square root of 2, right? And in the case of the generalized Simon's algorithm, what we'll get at the end of the first measurement, instead of this vector, what we'll get is the following one: 1 over square root of 2 power m summation um, y plus s I, where Si belongs to S. So we'll get this vector, which we'll call as y plus s, right? And then when you apply the Hadamard tensor N, after that our vector will change to 1 over square root of 2 power n minus m summation w belonging to s bar, s perp, and then minus 1 to the power w dot y, and then there will be w. So this will be the state at the end of the. So when we measure, you will get a vector w I belonging to S perp, right? And then hopefully, when you measure it, when you run this algorithm m times, or approximately order of m times, you will get this vectors w1, w2, and wm, such that wi dot si is equal to 0. So we get something which is in the orthogonal complement of S. And then what you have is a set of linear equations, which are so W1 transpose, W2 transpose, Wm transpose. So you have this. So these are, this is n minus m cross n-dimensional matrix. And then you have, we have S1, S2, Sm is equal to 0. So this is an n cross 1 matrix. So you get a linear set of linear equations just like before, and you can solve that to find these basis S1, S2, and Sm of S. Okay. So this generalization of a Simon's problem is also related to the hidden subgroup problem. So the problem is the following hidden subgroup. You have a subgroup H of a group G, and you have a function f from G to some set X, and Fx is equal to Fy if and only if X minus Y belong to H, right? So essentially the function is constant on the cosets, right? So this is X plus S, X2 plus S, and so on. And so the function is constant on this cosets, and the goal is to find this hidden subgroup S. Right. So a lot of the problems in quantum computing can be brought under this hidden subgroup theme, and which we will look at later.